media that you're supposed to turn your clocks forward tonight. In fact, in Arizona, that does not happen. So you are warned not to do that because we do not, in Arizona, there is no daylight saving time. So you can set your clocks forward when you get home. In any case, so tomorrow we'll start at the usual time, 9 o'clock in the morning, but standard time. So in any case, pleased to introduce Jeremy Teitelbaum from University of Illinois at Chicago.
So am I mic'd? Is this working? So I'm going to be speaking about the p-adic upper half plane, and there's, I guess, 5 talks, and the I guess the theme of the talks initially is just to talk about the geometry of this space, which is an interesting example that brings together some of the ideas that were talked about in the earlier lectures. And then to approach some analytic questions about the functions on this space. And there the theme kind of is the relationship between functions on this rigid variety and distributions on its boundary, kind of in the spirit of the Poisson transform in complex analysis. Partly, I think it's worth remembering that although the locally analytic manifolds, or the old-fashioned p-adic topology, where you just look at the natural topology on the p-adic numbers, it tends to take a little bit of abuse. I mean, it has many bad properties, like not, it's totally disconnected and so forth. But the fact is, you can't, I think, do rigid analysis without also doing that kind of analysis as well. So one of the themes which will come up in these talks is a kind of a duality between rigid geometry, or functions on rigid manifolds, and locally analytic functions. And this turns out to be a very, I think, common theme, that when you take, that these two kinds of analysis are related by duality. And we'll see some examples of this. And then in the last 2 lectures, more or less, I mean, the notes are written as 4 lectures divided into 5 parts. And so at the end of this, we'll make some connections with number theory, and there the sort of unifying theme is what are called L invariants. L invariants are kind of p-adic periods which appear in special values of L functions, and it turns out that the p-adic upper half plane and rigid analysis is a powerful tool for actually getting number theoretic information related to p-adic L functions. And so the last 2 lectures will kind of connect some of the rigid geometry that we've been seeing to number theory, to Iwasawa theory in the form of p-adic L functions. And a lot of that material will be based on ideas of Christophe Breuil and Henri Darmon. So historically speaking, we'll start with rather old material and end with rather new material, and the rigid geometry will somehow a little bit fade into the background towards the end. So let's start, though, just by talking about the p-adic upper half plane itself, which is, as I mentioned, a particularly interesting rigid analytic variety in the sense that Brian defined this morning. So I have some notation. I'm going to work with a finite extension of the p-adic numbers k as sort of the base field. I use OK to be its ring of integers and pi its uniformizing parameter. The standard absolute value means the p-adic absolute value. And I tend to write I tend to work with the additive valuation, which just means that you have the very simple job of converting all of the less than or equal to signs to greater than or equal to signs, and all of the infimums to supremums and supremums to infimums and so forth. And then you can transform all of the conditions about the absolute value into conditions about the additive valuation. So I apologize for that. A lot of what we're going to be talking about is intimately connected to this group GL2. I mean, just in the same way that the classical upper half plane is very intimately related to the group GL2R, or SL2R anyway. We're going to be working a lot with the group GL2 and with its maximal compact subgroup, or a maximal compact subgroup, GL2 of OK, nothing will happen to you if you just think QP and ZP, if that will make you happier. So to make the p-adic upper half plane, we start where we were this morning, in a very strong sense, with the projective line, or if you like, the affine line over the field K. Now, Matt was working with CP, so that's a hard field to work with. But we're going to work with an easier field, a locally compact field like a finite extension of QP or even QP itself, and start with the projective line. And partly I'm doing this, maybe this a little, partly it's kind of just to get us going. Partly if anybody does want to attempt to compare formulae, it sometimes helps to know which version of the projective line I have in mind. So the version of the projective line that I have in mind starts with a two-dimensional vector space represented as row vectors, and the group GL2 acts on the left by right multiplication by the inverse of the matrix. Now this is not my fault. This is Drinfeld's choice. And, but when I talk about P1, I mean this projective space over this two-dimensional vector space. And I'm going to use these psi0 and psi1, capital psi0 and psi1, to be the dual elements of the dual space, which are dual to these two basis vectors. And you should think of those as the homogeneous coordinates on this projective space. Now this choice has kind of a weird effect. I mean, the standard coordinate function z ends up getting acted on by the well-known Mobius transformation az plus c over bz plus d. And as we'll see later on, there are other effects like, well, I mean, it's the whole business. And actually, don't ask me any questions about this, because it's very easy to shake my confidence, and then this whole edifice will come crumbling down on this whole business of left and right actions. Okay, and just a little bit of notation. If we have a linear form in these homogeneous coordinates, psi0 and psi1, then it's called unimodular if at least one of its coefficients is a unit. And similarly, if you have a point of P1 represented in homogeneous coordinates, so I mean when I say unimodular, they should be integers, the two, and one of them should be a unit. And similarly, if you have a point of projective space, then the nice way to think of it is that you sort of normalize it by factoring out common denominators. So both of the homogeneous coordinates of the point are p-adic integers, and at least one of them is a p-adic unit. And then if you want to reduce such a point mod p, you can just reduce the homogeneous coordinates mod p and not worry about denominators and so forth. So now we can at least talk about what the points of the p-adic upper half plane are. It's going to turn out that the p-adic upper half plane, and it's been called in the literature various things. It's been called omega, but that's no good, because if you have any differential forms in the game, then you lose a valuable letter, so it can't be called omega. And it's been called H, but I didn't like H. So anyway, we have X. And the way you make this space is, if you want to know what its points are in a field L, which is an extension field of K, you take the points of P1 in that extension field L, and you throw out the K rational points. So in particular, if you like, you can think of L as some huge field like CP, and then the CP rational points of this upper half plane are what you get by taking CP and throwing out QP. Now, why would you think this has anything to do with the upper half plane? Well, G, remember, is GL2, and it acts on this space because if you take matrices with coefficients in K, it preserves the set that you deleted, and so it preserves the space that you have left. And I guess the comparison is to look in the classical case where you make the upper and lower half planes together by taking P1 over the complex numbers and throwing out the real points of that. Now that actually splits apart into two pieces, the upper half plane and the lower half plane. And then by reducing the group that you consider from GL to SL, you can basically forget about one of those components and just work with SL2 and the upper half plane. And that's what people usually do. In the p-adic situation, you can't do that. I mean, it turns out that this X of L, as I've described it, is irreducible as a rigid variety. It doesn't have an upper and lower half plane. There's lots of reasons why that's true. But also, the other thing to think about is that, I mean, C over R is small, right? It's two-dimensional. But, for instance, if L is CP, CP over QP is really huge. So, in certain ways, your picture of the classical upper half plane is not such a great view, not a great model for what the geometry of this space turns out to be. And we'll get a better picture of what the geometry of this space is as we go through the talk. And it turns out to be kind of closely connected to Matt's talk this morning. So in order to make this into a rigid variety, I have to give it all of this additional infrastructure that Brian talked about. That is to say, I have to describe for you what these aphanoid subvarieties are that describe the rigid topology. And so I'm going to give for you an admissible covering of this space, which will make it into a rigid variety. So what's the strategy? The strategy is, well, we have this big P1 of CP, and we have this little tiny compact set P1 of K inside it, and we want to get rid of it. And we do this by cutting holes in P1 of C around the K rational points. That gets rid of them, but it gets rid of too much. So we have to cut out smaller holes, and we keep doing that. We keep cutting out smaller and smaller and smaller holes that close down on this compact set. And each deletion of holes is one of these aphanoid domains. And I think I have a picture here. Not quite. I'll get to a picture soon. So to be a little bit more precise, by chance, our notations are quite similar. I can't take any credit for this, but how do you define the things that you cut out? Well, you take a point which has homogeneous coordinates, say y0, y1, and you look at this equation. So remember, bigger than or equal to with omega means less than or equal to an absolute value. So here what we're doing is we're fixing a point x0, x1, and this condition turns out to say throw out from P1 of CP the points that are close to this x0, x1, where r measures the distance. And whether you want to take the strict or non-strict inequality is whether you write the B or the B minus notation. So these are a typical hole that you might cut. N comes later. So here's N. Okay, so if you choose representatives for the points of your, let's say, P1 of K, P1 of QP, mod pi to the n. So here's some examples, right? You take AI comma 1, where the AIs are residue class mod pi to the n, and then you take 1 comma BI, but now the BI has to be divisible by P if you want to get distinct points. And you get a collection of points which cover P1 of K. Okay? And as you make n bigger, these disks get smaller, but there's more of them. They get smaller, but they still cover P1 of K. Oops. Okay, I'm getting the hang of this now. So the basic admissible open sets that we want to take are what you get if you take P1 and you throw out this finitely many balls. You can either throw out the open balls or the closed balls. If you throw out open balls, you get aphanoid domains, and if you throw out open balls, you get admissible open sets. In the end, it doesn't really matter. If you would like an exercise, then the exercise is to recognize this as an intersection of Laurent domains, for example, and using that, you can write down what the aphanoid algebra is for this complement, and I've drawn a picture of it here. So this picture, which is maybe not completely visible, this sort of shaded area on the outside, that's P1 of CP. And then you see these are the rational points, 1, 0, 1, for me, P tends to be 3. So 1, 0, 1 minus 3, 5, 1. These are the rational points mod 9 on projective space. And then you see I cut these holes and remove them. And then if you look more closely inside one of those holes that I cut out, well, inside, let's say, a congruence class mod 9 are the congruence classes mod 27, which you would also want to throw out. But you see this black stuff in between. Those are irrational numbers in CP, which happen to be congruent mod p to a rational number, but not mod p squared. So if you throw them out here, that's too much. So you cut smaller holes and you keep those, and then you keep doing this. You make the holes smaller and smaller. And if you take then these xn's, as n gets larger and larger, then the stuff that you've thrown out gets closer and closer to the stuff you really want to throw out. And by definition, the p-adic upper half plane is the union, or if you like, the limit of these admissible open sets. Is it union or intersection? No, union, yes.
Another way you could say it without mentioning CP is you have rigid analytic P1 over K, and this is just an explanation of why the complement of the K points is in fact an admissible open set.
Right. This construction takes place over K, and the only thing which is a little bit weird is this thing has no, when you're done, you construct something defined over K which has no K rational points because you've thrown them all out. But that's fine. Each of these aphanoids that you've gotten by deleting these holes is a perfectly good aphanoid variety defined over the field K. Now, as I said, a lot of my focus in these talks is on function theory, kind of global function theory on this space OX. And, on this space X. And so, because the space that turns out to be really interesting is the structure sheaf, the global sections of the structure sheaf on this entire space OX. So that's what I want to talk about now, is what are the entire functions on this rigid space that we've constructed. So each of these O of xn's, or O of xn, let's say the O of xn minus, those are the aphanoid algebras. Those are Banach spaces. They're like, we saw examples a little bit simpler, but of the same flavor in Brian's talk. They're given by, actually they're examples of these rational domains. You can write them down as some Tate algebra modulo some collection of relations. So they're Banach spaces, Banach algebras. But when you want to know what are the entire functions on this space, which is very, very large, then essentially what you're looking for are the functions on the big space whose restriction to every one of these aphanoid domains belongs to one of these aphanoid algebras. So what you're looking at is the projective limit over this increasing family of aphanoid domains of these aphanoid algebras. Now we saw, if you'd like an example, a simpler example, but which captures some of the flavor of this, you should look at the open unit disk. So the open unit disk, which came up this morning, is a very big rigid space. And it has an admissible covering by, remember, aphanoid disks, they're closed. They're the things whose absolute value is less than or equal to some fixed number. But the open unit disk is then a union of such closed disks of smaller radius, where you take a sequence of radii that approaches 1. And then the functions, the entire functions on the open unit disk are a projective limit of these Banach spaces. And just to give you some sense of the difference between a big space and a small space, on an one-dimensional aphanoid, one of these closed disks inside the open unit disk, a function will have only finitely many zeros. But on the open unit disk, you can have a function like the p-adic logarithm, log of 1 plus x, which converges on the open unit disk. It has only finitely many zeros in any aphanoid subdomain, but has infinitely many zeros on the open unit disk as a whole. So in that sense, that's the sense in which the open unit disk is large. The ring of entire functions on the open unit disk is not Noetherian, for example, because functions can have infinitely many zeros approaching the boundary. And in a certain sense, the p-adic upper half plane, it's not an open unit disk, but it has this flavor. And this ring OX is the ring of entire functions. You can think of such an element in reasonably concrete terms as being given by the limit of a sequence of rational functions, all of whose poles are contained inside the things that you cut out, and then which somehow converge uniformly on these affinoid subdomains. Now, when you have a big space like this, in a certain way, it's like an affine. These things, both the open unit disk, which really in some ways should be treated in detail before the p-adic upper half plane. These are kind of like affine varieties. Now, the term that you use in that situation is that they're what are called Stein spaces. In complex geometry, affine spaces tend to be Stein spaces. I think they are Stein spaces. And Stein spaces are close to being affine, or they're close to being the complex analytic spaces associated to affine varieties. And so there are two key properties of OX. The important properties of OX come out of sort of two properties of X. One is that it's a smooth one-dimensional Stein space. I'm not going to define that, but I'm going to tell you the consequences of it. And the other is more subtle, and it's functional analytic. And it's the statement that in these transition maps where you restrict from the affinoid domain that you got by cutting out a lot of little holes to the smaller affinoid domain that you got by cutting out fewer big holes, that map, which is restriction of functions, is a map between Banach spaces, and it's what's called a compact map. That is to say that the image of the unit ball in the first Banach space has compact closure in the image Banach space. And these two properties turn out to be important and also examples of general phenomena whenever you have one of these spaces which is constructed as an increasing union of affinoids. So what are the consequences of these things? So what is a Stein space, first of all? I guess I do tell you what a Stein space is in some sense. Whether this means anything, I don't know. Basically, all that I'm saying here is that, and I don't know why they're called quasi-Stein. Maybe someone can explain this to me. This is a definition due to Kiel. A quasi-Stein space is a space which is constructed by taking an admissible covering, which is just a union of affinoids, with the property that when you restrict on the function algebras back, those maps have dense image. Okay? That defines a Stein space or a quasi-Stein space. And as I mentioned before, that's kind of like being an affine variety. Okay? Like A1 would be an example of such a thing. And the two theorems that are true about Stein spaces in complex analysis are true also in rigid analysis. And they're called Theorem A and Theorem B. I'm not going to talk much about Theorem A, but Theorem B is the one that's kind of most important for my purposes. And it says that, and Brian hasn't defined coherent sheaf cohomology, so we'll find out what this means tomorrow, but there's no coherent sheaf cohomology on one of these Stein varieties. And so what that means basically is that there's no obstruction to analytic continuation on them. Okay? They don't have any periods. And we'll see where this comes. The place it comes up most directly is you can talk about the de Rham cohomology of X. Normally, you would have to do some kind of algebraic de Rham cohomology, but in a Stein space, de Rham cohomology just means take the one forms and mod out by the exact functions. Okay? So as a space, I should say, the one forms are just OX again, because there's a global function dz. That's my coordinate function. So a one form is just f of z dz, and an exact one form would be if you can integrate f back and still have a rigid function. Okay? The other consequence I mentioned, is this business of compact transition maps. And that has the following effect. First of all, this space OX is a projective limit of Banach spaces. And so the term for a topological vector space like that is it's a Frechet space. And this is, by the way, very similar to what happens in complex analysis. If you look at the ring of entire functions on, let's say, the complex plane, you again would get a Frechet space. And, but we're going to be interested in the dual of this Frechet space. So by definition, the strong dual of any locally convex topological vector space is you take all continuous linear forms on W and you equip this with the strong topology, meaning uniform convergence on bounded sets. If this means nothing to you, it's unlikely that I can do anything about this in these lectures, but there's a very nice book by Peter Schneider that does all of functional analysis over the p-adics in a very efficient way, and all of these things are described in there. But I'm really only interested in this one property, which is reflexivity. I mean, a topological vector space is reflexive if when you take its continuous dual with the strong topology, and then you take its continuous dual again with the strong topology, you get back where you started. That's a rare property of topological vector spaces, but OX has it. And the reason it has it is because it's a Frechet space, which is a projective limit of Banach spaces with compact transition maps. And since one of the things we're going to be doing is studying the dual of OX, this already indicates there's no information lost. You can pass back and forth between OX and its dual and recover the ring OX when you start out. Okay, a few more definitions here. Modular forms. So one thing you can do is you can take this big O space OX and you can have the group G act on it in various different ways. Basically, you can pick a weight, and I'm going to stick to even weights just because I didn't want to choose a square root of p, but there's no overpowering need to do that. And in my ridiculous group action, we have a left action of the group on functions by this formula here. And if you would take the space of entire functions and you give it this group action, that I call O of k. So it's the same space of functions, but the k just changes the group action, which we'll have to keep track of later. And when you take k equals 2, you get back the 1 forms in the usual way. I mean, if you apply g to f dz, f just changes in the usual way, and the dz contributes this automorphy factor in front. So O of 2 is the 1 forms with its natural g action, and then if you like, O of 4 would be the tensor square of that, and so on. So this is just like on the complex upper half plane. Schneider calls this the holomorphic discrete series, which might, for reasons that might make some sense later. And just to generalize what we said earlier about Durham cohomology, so remember that if you look at this map here for k equals 2, you have a map from O of 0, which is just the functions on the upper half plane with their usual action. And O of 2, I said, is the 1 forms, and the map is you take the first derivative of a function. Well, and this is true, this has nothing to do with rigid analysis. This is a nice exercise in the product rule and the chain rule, that if you take O of 2 minus k and O of k, and you take the k minus first derivative of a function, that it intertwines these group actions. So if you take the bz plus d and so forth, and then you take the derivative of it the right number of times, it changes the automorphy factor around. So we have a generalized notion of Durham cohomology from this exact sequence, namely, and remember, O of 2 minus k and O of k, they're all the same space. It's just a statement about the group action. But if you take the k minus first derivative of a function and take the co-kernel, you get what I call the kth generalized Durham cohomology. And the kernel is pk minus 2, and this is going to come up for the rest of the talks. Pk minus 2 means the polynomials of degree k minus 2 with the action that they have by virtue of being included in O of 2 minus k by this map. Okay, so that implies a certain group action on them. They're one variable, degree k minus 2, but the bz plus d removes the denominators and so forth. The center of the group acts trivially. And as I mentioned before, if you take k equals 2, you get the usual Durham cohomology. So what we're going to do in the next lecture is to study these spaces by trying to relate them to distributions on the boundary of the p-adic upper half space. That's basically the goal, is to study these spaces and relate them to functions in the, that are in the old-fashioned form of p-adic analysis, relate them to sort of locally analytic functions in the old-fashioned sense. But I want to do some more geometry before I talk about that. So let's go back now to trying to understand what the p-adic upper half plane actually looks like, and maybe make a little bit of contact with Matt's lecture this morning. So in order to do that, I'm going to talk about the Bruhat-Tietz tree for GL2 a little bit. So now we have a digression away from p-adic analysis and into kind of group theory, I guess. So when I talk about a lattice, I just mean in my fixed two-dimensional vector space V star, I just mean a rank 2 free OK submodule. And I put an equivalence relation on these things by saying the two lattices are the same if one is a scalar multiple of the other. And I make a graph whose vertices are the equivalence classes of lattices, so lattices up to scaling, and where I connect two lattices if you can find representatives for them, L1 and L2, so that L2 is a sublattice between L1 and pi L1. So I mean, this is so far maybe nothing at all. I mean, I have a lot of vertices and I have a lot of edges, but it's not clear what the structure of this would be in general. So here's a picture. It turns out that this graph is a homogeneous tree which has q plus 1 edges leaving every vertex, q being the cardinality of the residue field of k. I drew a picture here, and if I could find the pointer. Here we go. What I've done is mark the lattices. And so here's the basic lattice, which is spanned by psi 0 and psi 1. And then I put these adjacent lattices, all of which are between pi psi 0, pi psi 1, and psi 0, psi 1. And the reason that you get q plus 1 is because these adjacent vertices correspond to lines in this two-dimensional vector space over the residue field here. And there's q plus 1 of those because it's a copy of p1. Now this might sound a little bit similar to what we saw this morning. It will turn out that this piece of the tree, this is a tiny, tiny piece of the big, complicated tree that Matt drew this morning. But I want to view this as this thing not just combinatorially. I want to think of these edges as actually intervals. Okay? And you can alternatively describe this space not just as a combinatorial object which classifies lattices together with this adjacency relation, but as also classifying what are called norms on the two-dimensional vector space. And what's going to happen, I should say, is when you look at this as a space of norms, go back to my picture, we're going to get an interpretation for some of these intermediate points that lie on edges in the middle. Now, the interpretation we're going to get is not as general as the interpretation that Matt gets by Berkovich theory, but it's a step in that direction. So relating the two pictures will come later, but there is definitely a connection. So what is a norm? So for me, remember, this V star here is just a two-dimensional vector space, and a norm on it is a, that should, I think, be probably the other way around. A norm is a function to R. And remember, this is, I write it additively. So the only time it's truly a norm, it's multiplicative or additive in this case with respect to the scalar multiplication, and this is the triangle, the strong form of the triangle inequality. And we say these two things are equivalent if they differ by a constant, a fixed constant. So norms are related to lattices, namely if you have a lattice given a point, so x is this graph, remember, which is actually a homogeneous tree of degree q plus 1, Roman x. If you happen to pick a lattice, if you pick a point in that tree and it happens to be a vertex, then it corresponds to a lattice, right? And how do you get a norm out of a lattice? Well, the lattice has a basis, and you can write any vector in V star in that basis, and you can just take the infimum of the valuations of its coefficients in that basis. And in this construction, you see the lattice L is the unit ball in this norm, and you can actually go back. I'll say something about that in a minute. So that's how you associate to a vertex of the tree a norm. What about if you happen to pick a point on an edge? Well, you write the edge, your point, in barycentric coordinates relative to the two endpoints, which are lattices. Okay? So t now is just some number. And if you, I hope I did this right. So you still have a basis E0, E1 for L, but now you use the elementary divisors theorem, and since L prime is contained in L, and the quotient is just a copy of the field, the residue field, you can order the basis so that they're in this sort of standard form. And then you make a norm by basically, one way to think about this is you still have E0 having valuation 0, but you let E1 have valuation minus t, where t is this coordinate on the edge. And that also gives you a norm. And it's a theorem due to Iwahoria-Goldman, actually in higher dimension. I mean, they do this for the building of GLN, and they do it for norms on an n-dimensional vector space. Of course, they didn't know they were doing it for the building, because I think their work actually anticipates Brouhat-Tietz. But this is actually a bijection, namely, the points of the tree parameterize the norms on this two-dimensional vector space. And this, I won't talk about this. It's in the notes if you'd like to see how you go back and forth. The easy part is you take the unit ball. That's where you start. But it might happen that what you've got is not actually coming from a vertex, and then you have to figure out which edge you're supposed to, where on the edge you're supposed to be. And I think I won't go through it right now. But we now have an interpretation of all of the points on this tree, namely the vertices of the tree correspond to correspond to lattices, and the points on the edges correspond to norms that are kind of between the obvious norm that you get from a lattice. So you have two lattices, and you kind of mix those two norms together to get the points in the middle. Oh, here's a picture. This is the group action, but I think I'll come back to it. Let me just say. So the group acts on the norms just by their functions. So it acts on V star, so it acts on the norms by translation in this way. And it's a fact that it permutes the vertices and edges of the tree transitively. It's pretty easy to see that the stabilizer of, if you take V0, which in my previous picture is the standard, this is V0 here, it's the standard lattice. The stabilizer of that are the matrices which have integer coefficients. And the center is acting trivially, so it always fixes everything. And if you want to know this edge here, this is the basic edge. It joins this lattice xi0, xi1 to this lattice xi0, pi xi1. The stabilizer of that is this group which is kind of like gamma naught of p, except that it's a p-adic thing. Namely, it has lower left-hand entry divisible by p. And this group B has a normalizer, which is this matrix n, and what n does is it flips the edge. Okay? So the group acts on the tree, and it permutes the vertices and edges transitively, and then in the local area here, you have this inversion, which interchanges the edges, the vertices at the end of the edge. So that's the tree itself. The other important part of the tree are its ends. We saw these this morning also in a slightly different context. So what's an end? An end is a path in the tree which just goes like this, see? And it goes on and on and on until it comes to the end. And they're the same, two of these are the same if they are the same in the end, okay? So you can forget about what happens at the beginning, and it's only what happens at the end that matters. And so that's an end. And if you look at the ends, you get, they form a topological space. And this is, if we were in the Berkovich situation that was talked about this morning, you remember that the ends here, there were all these different kinds of points. But, and we had this topology given by the visibility. So you can actually put the ends of the tree, they have a topology where you stand on this edge, and you look out this way. I guess you stand on this edge, maybe. You look out this way, and you see all these green ends out here, and that's an open set. Okay? So each edge of the tree gives you an open set in the end. So this one here gives you this big open set, right? And this one here gives you this little green open set. And this is a compact and totally disconnected space with this topology. So now this, by the way, so far this is just about the tree, right? There's no p-adic analysis here. Now, if you think about what these edges, what the vertices represent, to have a path like this, right, that goes down, 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 is to have a sequence of lattices, each nested in the preceding one. And if you have such a sequence of lattices, you can intersect all of them. And when you intersect all of them, you get, it turns out, a one-dimensional subspace of your two-dimensional vector space. And that's a point of this projective space, projective line. And this gives you a way to identify the ends of the tree with P1. And that turns out to be a homeomorphism. The ends of, I won't go through the proof. It's all in the notes. But this gives a homeomorphism from the ends of the tree to the projective line over K. And if you trace back through all the definitions, this basic edge, which corresponded to this pair of lattices, turns out to correspond to this open ball centered at the point 0, 1 and of radius 1 in P1 of K, which I think would have been called this point right here, I think, will turn out to be the Gauss point, okay, once we make some connection between these two pictures. And this map commutes with the action of the group. So the tree, the ends of the tree really are P1 of K in a pretty strong sense. So this is a little bit more about the group action, namely, if you want to know the stabilizer of an end, it's a Borel subgroup. Now you have truly equal to 0 in the lower left-hand corner, not just congruent to 0. And if you want to recognize the ends as a homogeneous space, this is the way to do it. P1 is G mod P. P is this group. And if you take your point in homogeneous coordinates and you stick it in the first column in this way, and then let G act on the left, just by multiplication, you get back the group action that we've been using. And similarly, if you like to keep track of the group action, the edge here, in this picture here, you take the orbit under this Iwahori group B, that gives you the open set for this standard edge. And the other edges, other ends, are just G translates of that. So any ball, any one of these disks in the ends is a G translate of this sort of standard open set. It would be interesting to figure out on the big picture of the group acted on the tree, the complicated tree that Matt drew, and you could try to figure out what the group action on that looked like. Whoops. So now the last thing, this is funny that this slide is blank. It used to say, I believe, the reduction map, but okay. So now I want to connect these two things that I've been talking about, which are possibly not related in an evident way. That is to say, on the one hand, this p-adic upper half space, which has this Fréchet space of rigid analytic functions on it, on which the group acts in various ways. And then this tree, which parameterizes norms and whose ends are P1 of K. And so far, the only connection you might be able to see between them is that in each case, the boundary of the two spaces is the same. Somehow, the part we deleted from the p-adic upper half, we deleted P1 of K from the projective line to get the upper half plane, and that's exactly the ends of the tree, and those somehow match up. So what about the rest of it? Well, there's a sort of easy map from the points of the p-adic upper half plane here to norms. Namely, suppose you have a linear form, L, and you have a point in x of CP. So that means it's a point, basically, it's in CP but not in K. Just evaluate, so L is a linear form, it's in V star, just evaluate it at that point. So the fact that that AB belongs to x of CP is really, to say it in a fancy way, means its coordinates are linearly independent over K. Because how do you tell if you're in projective space over K? Well, you could just, if I wanted, I could have just written 1B. And this B better not be in K. So if you take a linear form which has coefficients in K, and you evaluate it at a point whose coordinates are linearly independent over K, you do not get 0. Okay? Therefore, when you take the valuation of that thing, you do not get infinity. And therefore, you get a norm. Okay? And this is called the reduction map. The places where this fails to be a norm and is only a semi-norm would be the places where L vanishes, and that would be precisely at the rational points for some L. And this reduction map, for trivial reasons, commutes with the G action. Namely, G acts both on the upper half space and on the tree, and if you think of the tree as a space of norms, the action is completely compatible. So now we have a direct connection between the p-adic upper half space and the tree. So I believe it's the case that, I mean, if you look at this from Berkovich's point of view, this map has, I mean, this tree that I've drawn is a small piece, right, of the complicated tree that we saw this morning. And what Berkovich actually proves is that if you look at the p-adic upper half space in his category, then this is a retraction. I mean, the tree is actually in the Berkovich space. Okay? It's embedded in the Berkovich space, kind of as the piece of Matt's picture that just corresponds to the edges that go out to the rational points. But we don't actually need that in this picture. We're just going to think of them as sort of separate objects that are related. But if you want to somehow see the force of Berkovich's ideas, what we've seen as a kind of an interesting relationship becomes much more than that from the Berkovich point of view. Now, I mean, we'd like to know something about the geometry of this map. I think I'm going to skip ahead a little bit. I may start here in my next talk, but I want to show you this picture here. This is a picture. This is how to actually think of the relationship between the p-adic upper half plane and the tree. So there's this reduction map, right? And the reduction map so the red stuff, see the red stuff, this thing here? This is the p-adic upper half plane. And it maps down to the tree, which sort of runs down through the center of it. Okay? And why does this make any sense at all? Well, you see this little picture here? This should look familiar, because this is one of the pictures that Matt drew this morning. He only cut out 2 holes, but I've cut out 3. So we take a ball, and we cut 3 holes in it, right? And in the Berkovich picture, that sort of corresponds to taking this point and sort of looking back from these 3 balls towards this bigger disk, and then we've also cut out the stuff at infinity, so we're looking back down this way. But I mean, if you don't like that and you just want sort of more impressionistic notion, then you should think of this somehow, right? I mean, these edges here, they stick into those holes, except one of them, which corresponds to the outside. And you can wrap this thing around this little link of a vertex as a tubular neighborhood, right? But remember that inside these holes that we cut out, there were smaller holes that we cut out. And inside those, there were smaller holes that we cut out. And so you get this branching of the tree as you go on. And I mean, one of the ways in which this is actually a really good picture is to go back to the de Rham cohomology. I mean, no one objected, but of course, what's the de Rham cohomology of the classical upper half plane? I mean, it doesn't have any, right? I mean, it's contractible. So what is this thing we're calling the p-adic upper half plane? Why is there any de Rham cohomology in it at all? But from this picture, you see that I mean, if this has got any sort of meaning to it, you can see lots of cohomology here, right? Because you see all these loops around the edges of the tree. And it actually will turn out, then we'll see this, that kind of accounts for the de Rham cohomology of this upper half plane. I mean, it acts as though, from the point of view of de Rham cohomology, it really were a tubular neighborhood of this tree. So this is a good picture to have in mind. And then if I have time, what you can prove, and that's the couple slides that I skipped, is that if you look at the fiber of the reduction map, so you ask yourself, which points reduce to one of these edges and which points reduce to one of these vertices, you find that the points that reduce to a vertex are a region that look kind of like this, and the points that reduce to an edge are annuli. They're points where you sort of say absolute value z is between A and B. And that's sort of what you'd expect, right? I mean, if you cut this off and flatten it out, it's an annulus. So I guess I'll stop there and pick up tomorrow.